Hello there. Welcome back. In the last lesson, I introduced you to sequences and series, and I showed you what it means for a sequence or a series to converge or diverge. Well, some amazing mathematicians have developed some tests to help us to determine if a particular series converges or diverges. We're going to learn three of those today: the geometric series test, the nth term test, and the integral test. To refresh, a geometric sequence is one in which the same number is multiplied to each term to get the next term in the sequence. The number you multiply by is called the common ratio. The nth term of a geometric sequence with the first term a sub 1 and common ratio r is given by, well, it can look like a lot of different things. So let's break this down a little bit. We're going to write an expression for the nth term of this sequence in three different ways. So first of all, let's figure out what's going on with this sequence. If you look from one term to the next, can you see what the common ratio is? The common ratio is 2. So for each of these, see how it's like r to the n minus 1, r to the n minus 2? Let's go ahead and plug in a 2 for each of those. Now we've got a sub 0, a sub 1, and a sub 2 that we have to fill in. Well, the first term we're given 3, that's a sub 1, so we can put that in. And then the second term we're given is a sub 2, so we can plug that in. What's a sub 0? Well, if you look at the a sub 2 term, it's 6. If you look at the a sub 1 term, it's 3. So we just have to kind of use our common ratio going backwards. Instead of multiplying, we've got 6 divided by 2 is 3. So 3 divided by 2 will give us our a sub 0 term, which is 3/2. Let's try another one. So this time, we're getting smaller. What would our common ratio be on this one? Looks like each time we're dividing by 5 or multiplying by 1/5. So that's our common ratio, 1/5. So let's plug in each of those, okay? Then we can figure out our a sub 1 term. A sub 1 is 25. And a sub 2 is 5. So to get our a sub 0 term, we've got, let's see, 5 times 5 is 25. So 25 times 5 gives us 125. So we're doing this just because you may see an nth term of a sequence written a lot of different ways. We're going to start with the geometric series test. So this is a geometric series. And what we know is that a geometric series diverges if the common ratio, the absolute value of the common ratio, is greater than or equal to 1. If the absolute value of the common ratio is between 0 and 1, then we know that a geometric series converges to, whoa, what is that? Well, this is really special. For a geometric series, we actually can know what the series converges to. That's not the case for all series. But what this says is the infinite series, when you add all the terms up, you actually know what it adds to. It adds to a to the rk. That is the first term of the series because we have n starting at k, and we have our a common ratio to the k. So it's the first term over 1 minus the common ratio. It's so cool how that works. So we'll practice this. Evaluate the series or state that the series diverges. Sometimes the first thing we have to do is rewrite a series to make it look like what we're used to. So 3 over 4 to the n. Kind of tough to see the common ratio there, but if I pull out the 3 in front, I can rewrite it as 3 times 1 over 4 to the n. And now I can really see it. I have a common ratio of 1/4. That is less than 1. So I know that this series converges by the geometric series test. I can also figure out the sum of the series. I know that my n, we're starting at 0. So my first term, let me clean this up. My first term is going to be 3 over 4 to the 0. I just plug in the first n that they told us. So 3 over 4 to the 0, that's just 3. So I take my first term and divide it by 1 minus r. So that's 3 over 3/4, which is 4. So if I add up all of these terms to infinity, I get 4. Okay, here's another one. Again, the first step is trying to figure out what the heck is the common ratio if this is a geometric series. Well, let me rewrite it for you a little bit first. 3 to the n plus 1. I can rewrite that as 3 times 3 to the n, because that's 3 to the 1, right? Okay, now look at here. There we go. There's my common ratio of 3/4. So common ratio of 3/4, that is less than 1. The absolute value, I should say, is between 0 and 1, if I want to get technical. And so we know that the series converges by the geometric series test. And because this is a geometric series, I know what it converges to. Interesting, this time my terms start at n equals 2. So to find my first term, I'll plug in 2 to the n's. And I get a first term of 27 over 16. All right. So to find what the series sums to, then I take my first term, 27 over 16, and divide that by 1 minus r. And I get 27 over 4. There's the sum of my infinite series. Okay, this one's already set up nicely for us. We can just see right off the bat that we have a common ratio of 4/3. That's bigger than 1. So this series diverges by the geometric series test, and we're done with that one. The next test we're going to look at is called the nth term test for divergence. If an infinite series converges, then it must be the case that the terms are all heading towards 0. Now, if you have a sequence and all the terms are heading towards 0, you don't necessarily know that the series converges. It could converge or diverge. But what we do know is if the terms are not heading to 0, then the series is going to diverge. It's just going to grow and grow and grow. That's why this is called the nth term test for divergence. So example 4 here says use the nth term test to make a conclusion about divergence. So this guy right here, that's my a sub n. If I'm going to use the nth term test, then I'll take the limit as n approaches infinity of a sub n. Okay, so as n approaches infinity of this one, there we go, I go to 3/5. That's not 0. Okay, so the series diverges by the nth term test. Let's try another one. 1 over n. Again, this is my a sub n. And if I take the limit as n approaches infinity of that, oh, that goes to 0. That actually doesn't tell me much. I can't make a conclusion about this. And this is actually an interesting one. Let me graph it for you. This is what we call the harmonic series, and we're going to learn more about this in some upcoming lessons. And this series actually diverges. You can see that the terms are getting smaller and smaller and smaller and smaller and smaller, but basically the terms don't get to 0 fast enough for the series to converge. It's really interesting how that works. You can look up various proofs on that one if you are so inclined. All right, let's look at C. We have an a sub n term of 2 to the n plus 2 over 2 to the n plus 3 plus 1. There's so much going on there. How do you make heads or tails of it? Well, we're going to rewrite the top and the bottom. We're going to break up these little guys a bit so we can see what's going on. So 2 to the n plus 2, I can rewrite that as 2 to the n times 2 to the 2. And 2 to the n plus 3, I can rewrite that as 2 to the n times 2 to the 3. Now I can take the limit as n approaches infinity of that, and the 2 to the n's cancel each other out. Now, why did I also cross out this plus 1? Well, you can imagine, as you're going to infinity, like huge, 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 huge numbers, a plus 1 isn't going to really matter much. So we'll just not worry about it. So this goes to 4 over 8. That's not 0. So this series diverges by the nth term test. Oh, we've got another factorial. Okay, so how do we do this one? Here's a trick to make it a little bit easier. We're going to divide the top and the bottom by n factorial. So if I divide the top by n factorial, and then each term of the bottom by n factorial, I can kind of get a glimpse of what's going on. This I can reduce to 1. This goes to 2. And then 1 over n factorial. As n approaches infinity, what does this go to? It goes to 0. So this whole thing goes to 1/2. Okay, that's not 0. This guy diverges by the nth term test. The next test we're going to look at is the integral test for convergence. Now, this is a simple test that can be used if the problem is easy to integrate. If f is a positive, continuous, and decreasing function for all x greater than or equal to some k, and a sub n equals f of x, then, okay, so this a sub n here is actually a function. And if we have a series, an infinite series for that a sub n, then we can actually look at an improper integral of that function going from some constant to infinity. And the cool thing is that either both converge or both diverge. So again, it has to be a positive, continuous, and decreasing function. Whatever the improper integral does, the series does the same thing. Now I'm going to show you the proof for this, and you don't have to know how to come up with this proof, but it's important to see where this integral test comes from. So I have a positive, continuous, and decreasing function. And let's start filling in some of the things we know. We've got an x value of 1 and then an x value of 2. And if I continue that on for a really long time, I could have an x value of n and then an x value of n plus 1. And if I create all these little rectangles, remember Riemann sums, the top left of this would have a y value or a height of a sub 1. And then this one would have a height of a sub 2, a sub n plus 1, and so on and so forth. So the width of each rectangle is 1. The height of each rectangle is a sub n. Therefore, the area of these rectangles is a sub n. So what I know about this is all of these rectangles overestimate. And if I add all of these a sub n's up, then the sum of them all is going to be greater than the actual value of the area under that curve. Now let's look at this one. Same thing, I can put some x values in here, 1, 2, n plus 1. And then I've got some y values or the height of each rectangle. Now, the first time the rectangle hits the graph is at a sub 2. And then I'd get an a sub 3, and then continuing on to a sub n and a sub n plus 1. If I add up all of these rectangles to get the area under the curve, I am underestimating. Now, I have a width of 1, I have a height of a sub n, and an area of a sub n. So when I add all those up, add all of these up, whatever I get is going to be less than the actual value of the area under the curve. Now, I'm pretty close to being able to compare these a sub n expressions, but this one starts at n equals 1, and this one starts at n equals 2. So I need them to be the same. So what I can do is add this a sub 1 to both sides of this one. And when I do that, now I have an n starting at 1. And then I just have to, there we go, add the a sub 1 to that side. Okay, stick with me here. Now, if I were to take the limit as n approaches infinity, then n and n plus 1, it's all going to infinity. If I look at all of these expressions, the smallest one is this one, from 1 to infinity, f of x dx. And then the sum of the infinite series would get stuck in the middle. And then the largest of all those expressions would be this one, because I've added that constant to it. So if this guy converges on the left, then this one also converges. We've just added a little constant on the end, which means the one in the middle, this is the series that we're interested in, that has to converge. It's squeezed into converging. The same would be true that if this integral diverges and this integral diverges, all we've done is add a constant, then the series also has to diverge. So there you go, the proof for the integral test for convergence. Now let's see how it actually works. Determine whether the following series converge or diverge. Okay, well, if I had to integrate that, well, I probably could. So let's let a sub n equal f of x, which equals this function here. I've graphed it there for you so you could see it. It is a positive function for x greater than or equal to 1. It's continuous. Is it decreasing? Without the graph, how would you know if the function is decreasing? Well, let's take the derivative. If you take the derivative of f of x, you get a negative derivative. Therefore, this function is actually decreasing for all x greater than or equal to 1. So we have met the conditions for the integral test. Now we will go ahead and integrate the function. So we'll take the limit as b approaches infinity. We're integrating from 1 to b of 1 over 3x plus 4. So when we integrate that, we get 1/3 natural log of 3x plus 4, evaluate from 1 to b, and then we're still taking the limit as b approaches infinity. So if that b is going to infinity, then that whole expression is going to infinity. So this integral diverges, therefore the infinite series also diverges by the integral test. Let's try this one. 1 over n cubed. So we'll let a sub n be the function 1 over x cubed. It is positive for all x greater than 1. It's continuous for all x greater than or equal to 1. Is it decreasing? Let's take the derivative and see what's happening. So if we take the derivative of x to the negative 3, we get negative 3x to the negative 4th. We have a negative derivative. It is indeed decreasing for all x greater than or equal to 1. And now we can just go ahead and integrate this. So the limit as b approaches infinity, okay, so we're going from 1 to b of x to the negative 3. We get negative 1/2 x to the negative 2, evaluating from 1 to b. And then as b goes to infinity, that guy goes to 0. So the whole expression goes to 1/2. So this integral converges to 1/2. Therefore, the series also converges by the integral test. Holy Moses, that was a lot, but you hung in there with me, and I applaud you for that. So next time, we'll learn a couple more tests, but before you get to the next video, please practice, practice, practice using these to get a good handle on them. I'll see you next time.